Hello. You see, I have a ball here, and if I throw this ball up, woo, and throw it back down, I caught it, but I could also throw it up to where it hits the ground like that. So we all know what a ball does. We throw it up, it goes up, it hits a maximum height, and then it comes back down again. And if there's a ground there, it'll hit the ground. It'll hit something, usually on the way down. But what if we wanted to graph the position versus time at every spot while the ball goes up and comes back down again? So this is Climb Time, and today we are going to look at the graphs of position versus time. So let's say we have a y-axis and an x-axis, looks something like that. And I throw the ball and it goes up, it comes back down. Let's make the x-axis a little bit bigger like that. And it looks something like that. And so this is the x-axis, time, and this is the y-axis, which I'm going to say s. S is the general variable that we use for position. It could be a horizontal position. It could be a vertical position. In this case, it's a vertical position. It's the height. And so S is just sort of a general position variable. And there are some useful spots along this graph. One useful spot's at the top, and that's where it reaches its peak. Another useful spot is when it hits the ground, which is right here. Another useful spot is right here, which is going to be the initial height. So we have the initial height, we have the peak, and we have where it hits the ground. So those are three very interesting and useful spots to take a look at. So this is going to be your peak. And at the peak, something interesting happens, and that is that it changes direction. It's going up, then it hits a peak, and then it starts going back down again. And then this right here is going to be where it hits the ground. And then this part over here is going to be its initial position right there, initial position. So these are the three most interesting points on a graph when we look at a ball going up and coming back down again. All right, well, what happens if we want to connect 2 points together? Let's say here's our position, here's our time, same graph. And again, here's our initial position, here's our peak, and here's where it hits the ground. What happens if we want to connect 2 points together like this and make a line? What happens then? Well, each one of these positions, each one of these points has an x and a y value. So this right here has an x and y value. This right here has an x and y value, and this right here has an x and y value. And so this is going to give us a certain time at which it hits the ground. And so I don't know what time it is. Maybe I'll call it T3 because I don't know what time it is. And when it hits the ground, it's going to have a 0 height because height is on the y-axis, and so the y value is 0. This one over here is going to have a non-zero height, but a 0 time. So the point looks something like this. We have 0, and then we have an initial position, which we often call S of 0, and that's its initial position. And then we have a time at which it hits the peak. So right there, it's going to be some time. Maybe I'll call it T, probably should have called this T0, T1, and T2, but anyhow, I'll call this T2. So T2, and it's going to reach a height, which I'm going to call S2. So that's going to be the X value and the Y value. And so that means the Y value is going to be S2, which is going to be the function value when T2 is plugged in, if we have a function for S. Now, if we draw a line between those 2 points, and we want to look at the slope of that line, the slope of that line is going to be the change in Y over the change in X. That's how we find slope. But in this case, my Y value is S, and my X value is T. So my slope is change in S over change in T. And so if I look at what my change in, so I look at this point here, so I look at the difference between my X values, my run, if you will, which is actually T values in this case, because on the X axis I have times. So this is my change in T right here. And then my difference in height would be right here. And that's my change in S. So change in S is this, change in T is that, that's my slope. And so what we call that is velocity, and more specifically, average velocity. So this is what we would call the average velocity of this ball between those 2 points. So the average velocity is defined as, and this is what we use for variables, AV. Some books use a V with a bar above it. And average velocity is going to be change in position over change in time. That's how we define the average velocity. So the slope of a line between 2 points on the position curve is the average velocity. Now, I want to point out something really quick, and that is what happens if my position is the same between 2 points. So it goes up, it comes back down again, and let's say we look at the difference in position between these 2 points, which have the exact same y position. So in this case, your average velocity is going to be, let's go back to blue again. My average velocity is going to be the change in position over the change in time, but the change in position is 0 because that position, that y value, that height, and that height are the same. And so therefore, your average velocity is 0. So that doesn't mean the ball's not moving. The ball was moving. As soon as I let go of it, it's moving, it's going up. It hits a peak, and at the peak, it stops momentarily, but then starts moving as it comes back down again. So the ball is continuously moving, but the average velocity between these 2 points, between that point and that point, is 0 because the position was the same. There was a position when I initially launched it, and then it eventually hit that position again on the way back down. And so because the change in position is 0, based on the definition of the average velocity is 0. So what I want to point out is average velocity is a little bit different than your instantaneous velocity.